Hello and welcome to this session where I'll talk you through this exercise where we implement a recommender system using matrix factorization. So you should think of a recommender system as a model that takes as an input a user and, let's say, a movie, and the output of the system is the predicted rating that this user would give to the movie. So this could be any model in principle. If you had features about users and about movies, you could just train a model to do this. But the challenge here is that for all the users and all the movies, we don't really have features. We just know that it's user 13 and movie 512. So, just based on those numbers, you can't say anything. So what recommender systems do is kind of implicitly derive features from the other recommendations of a user. Like, if I always like science fiction movies, it can look at other users that also like science fiction movies and recommend more of those to me. Okay, so let's go through the notebook. We'll start by loading a dataset with movie ratings from Movie Lens dataset. This dataset consists of 100,000 ratings, and a rating here is a pair of a movie, a user, and a given rating. So the way we store it here is as 3 arrays of the same length, like which movie, which user, and what did the user think about the movie. You don't have to do anything here, this just loads the data. Okay. Next, we want to look at the distribution of how many ratings each user gave and how many ratings there are for each movie. You'll see that there are some movies or users that are just very rare in this data set. And if you only have one example rating for a movie, it's too unreliable to make predictions out of it. So in the next section here, we'll remove entries from the dataset that have too few ratings. So we remove movies that don't have enough ratings available. Okay, so you have to fill in the blanks here. And the tests can tell you when you did a good job. Okay, next, we'll split this dataset into a train and a test split. In this case, we'll use 10% of the data for testing and 90% for training. That just means we'll have some movie user pairs for which we have a rating available, but that we don't use for optimizing the model. Okay. So the way we've thought about this dataset so far is as 3 lists of information, like which user, which movie, and which rating. But you can also think of this in matrix form, which is quite common, where the matrix is basically on the x-axis we have movies, on the y-axis we have users, and the number inside the cell is the rating that the user gave to the movie. This matrix, like based on this training set, for example, will have lots of unknown cells because we don't have the ratings. But the challenge, you could see the challenge of recommending as filling in this matrix. Like if you fill in this matrix, you know all the possible ratings that any user could give to any movie. Okay, next we'll start to really make predictions. And we'll compare a couple of baselines to this matrix factorization solution. And all the methods that are implemented have this form. Like they will be a class that looks like a predictor. Like here you will already see there is global mean predictor. But this is just like an example of how it functions. You create the class, and when you create it, you pass training data. So what you can do in here is optimize the predictor, or like train it. It also the predictors also have a call method implemented. That means you can use it as a function, kind of. This is an example of how you would use it. You create the predictor with training data, so this could train it, for example. And then to make predictions, we call it like a function that's using this call with new data you want predictions for. Okay, so here the first example you'll implement is global mean predictor. That means we'll just look at the average prediction that was given by any user to any movie, and that's what we'll say. For any user movie pair, we'll just say, I think you like it 3.5. That's a pretty stupid baseline, but it's good to have those. It's easy to implement, and it gives us a number of quality we can compare our other methods to. If they perform worse than this, it's no good. The way we'll compare method is using mean squared error. Like over the test set, we'll look at the average squared error of the predicted rating and the real rating, and you'll have to implement that here. Okay, now we'll get into slightly more serious baselines. One here is called the user mean predictor. What it does is, for any movie user pair, the rating that we'll give is the average rating of the user over all movies it has seen. So if you tend to hate all movies, we'll guess that you'll hate the next movie too. And if you like all movies, we'll guess that you'll like any other movie too. Okay, so there's a question here. Is this working better than predicting the global mean in terms of error? What do you expect? Like, maybe you should think of this before actually coding it up. There's also a question, why would always predict the user's mean be pretty useless in practice? So think about that. And then we can move to the next predictor. This is the movie's mean predictor. It's basically the same thing, but now we will return the average of all movie ratings for a particular movie, irrespective of the user. So this can be a better model, I think. And you should think for yourself, like, under which assumption is this a good model? Yeah, I'll leave that question to you. And again, you should compare the quality you get here to the two we have seen above. And you should think for yourself if that matches your expectations. Okay, next we'll get into the real meat of this exercise. You are going to implement matrix factorization. And let me just go over the model you're expected to implement. So to each movie I in the dataset, we will assign a d-dimensional trainable representation vector mi. Okay, so these vectors are going to represent the movies, and if movies are somehow similar, meaning that the same users like them, those vectors should also intuitively be similar. And in the same way, for each user j, they will also have a d-dimensional representation vector uj, and if users have similar taste, those should also be similar vectors. Okay, so we can think of those as like separate vectors for each user, but you can also stack up all those vectors into matrices. Like, there's a movie representation matrix M. It has a number of movies rows and D columns. And you can have a user representation matrix U, and it has size number of users by D again. So this model, after we've optimized those representations, and we'll see later how to do that, it can predict the score that a user J will give for a movie I as the dot product between those representations. Like, if the user representation and the movie align, then this is a high number. You could think of this as like a kind of cosine that is not normalized. Okay, so again, and this is formulated as a model now. It has inputs I and j. It looks up these embeddings or representations, and it gives you a number. But you can also simultaneously express the predicted scores for all movies and all users as, this matrix we've discussed before, like a number of movies by number of users. And, combining all those predictions that are dot products, we'll get a matrix product, and that is mu transpose. And it's this interpretation as a matrix product that gives the name matrix factorization to this type of model. Okay, so the last thing we need to discuss is how are we going to optimize those movie and user representations. We're just going to do that by optimizing the predicted ratings over the training set. So we have an average over the training set, over like triples of user, movie, and rating. We'll make a prediction of the movie and the user and compare it to the real rating. This gives us like one number per triple, and we average those. That's the loss. Okay, so here you're expected to initialize the movie and the user representations. Normally you should, like if you want to write good code, you should probably put the training code in here. But for now we'll skip the training and we'll implement that separately later so we can go step by step. In the call method here, you should implement this dot product prediction for, and it should give one rating for each entry in the test data set. Okay. This is a much more complicated model and then the baselines. So you should really compare the results you got here to the results above. And if this is not as good as before, either you made an error or you should consider using a simpler model, because simpler is always better. Okay. Oh, sorry. Here it shouldn't work yet because it's not trained. That's what we'll do next, and then you should compare. Okay. One way to optimize this model is to optimize those representations using stochastic gradient descent. So the stochasticity comes from like sampling one triple of movie user rating at each step, or in this case cycling through it in epochs. And then, once you sampled one of these terms, you compute the gradient and take a small gradient step on M and on U of that particular entry we sampled. That's what you'll optimize here. And to check if you did well, you should expect the test error to go down below 1.0. So that's slightly better than the other models. Okay, because this is stochastic gradient descent, the results can be quite sensitive to the learning rate you used and the weight decay parameters. So I forgot to talk about weight decay. Weight decay means we'll add you've seen this before, it's the same as L2 regularization, and it means we would like the representations M and U to remain small. So we add a loss term that is squared entries of M and squared entries of U weighted by a regularizer term. I'll update this in the notebook so you have it written out here. Okay, so another way to optimize this is using alternating least squares. And here, instead of stochastically sampling triples movie user rating, what we'll do is fix all the user representations. And if you do that, if you fix those, then optimizing for M is just a quadratic problem, and which we can exactly solve. And if you, on the other hand, keep all the movie representations fixed, we can optimize all the user representations, then this is just a quadratic problem. So that's and the alternating part of this is that we'll go iteratively between the two. So you fix the user representations and then perfectly optimize the movie representations. And then in the next step, you fix the movie representations and perfectly optimize the user representations. And then you go back and forth between those. So we expect this to give the best results. And it's not that you couldn't get this with SGD, but it's just a bit more tricky to tune. If you use the default parameters we gave here, this should work better. Okay, good luck with this, and let us know if you have any questions on the forum.